Hello everyone. Uh, Welcome to another lecture as part of our Computational Heat and Fluid Flow ME 6151 course. Let's get started. So today, in the last lecture, we looked at the influence of secondary gradients on the coefficients, right? We kind of reasoned out that secondary gradients create negative coefficients which may lead to oscillations. As a result, it is kind of a good practice to have a good quality mesh, right, which is kind of as orthogonal as possible. And then we have also looked at the solution algorithm for implementing a diffusion equation on unstructured meshes, right? We said instead of going through a cell-centered approach, if we traverse the mesh through a phase-based approach, then access the cells and fill in the coefficients, and then go to the cells and calculate the central coefficients, the AP coefficients, and so on, then that is a better way of solving the unstructured problem, right? That's what we have kind of discussed in the last class. So we have also finished the chapter 3, which is on the diffusion equation. So today we're going to look at the next chapter, that is the chapter on convection. Essentially, we're going to look at the convection and diffusion as part of chapter 4. So the two specific things that we will discuss today is the first is the discretization of the convection term, right, which we have not seen till now on a structured Cartesian mesh. Okay, so we will kind of go back to the structured mesh to start with. Then we will learn how to discretize the convection term on a structured mesh. Thereafter, we will introduce the unstructured or a non-orthogonal mesh. Okay, so that is kind of the steps we will take, and we will also look at a particular scheme for discretizing the convection term, that is the central differencing scheme. Okay, so these are the two things we're going to see in today's lecture. All right, let's get started. So we will start with our general scalar transport equation. Okay, so the general scalar transport equation is written here, right? So basically, the general scalar transport equation or the convection diffusion equation, as it is known as, right, is written here, in which the first term is the unsteady term, that is partial T rho phi, plus the second term is the convection term, that is del dot rho u bar phi, and on the right hand side we have the diffusion term, that is del dot gamma grad phi plus s phi, right? So this is the equation we have kind of started off with. We already know how to solve the or take into account the unsteady part and the diffusion terms, right? These two things we already know. The only thing we did not know is how do I now include the convection term in there, which will allow us to solve the entire general scalar transport equation, right, or the convection diffusion equation. Okay, so so that is the thing. So essentially we already know how to discretize this part, right? Okay, now here when we solve this problem, you see that we have a velocity field that is introduced. So as far as the convection diffusion is concerned, we will assume that u bar is a known quantity. Okay, so that's what we will assume. We will assume that u bar is known. Okay, that means the underlying flow field is known. However, let's say in a real flow field, u will be an unknown, right? This will be an unknown which we have to calculate. Okay, and the question we are interested in basically is how is this phi that we have, right? How is this phi getting transported in the presence of a known flow field? So essentially u bar is known, and how is my phi getting transported? That is the real question we are asking. And what we do is initially we will assume that we don't have the unsteady term in here. Okay, so we'll only solve for a steady convection diffusion equation. Okay, later on, of course, we can introduce the unsteady part as we have done for our pure diffusion equation. Okay, so that's what we would be doing. So let us start off with the two-dimensional structured mesh as shown here, right? This is the same mesh we had before. Essentially, we have a Cartesian mesh with either uniform cells or non-uniform cells, and we have the primary cell P on which we are focusing our discretization on, and then we have an east cell, west cell, north and the south cells, and the corresponding faces are the little e, little w, little north and little south. Okay, and the width of the cell in the x direction is delta x, and the width of the cell in the y direction is delta y, and of course the other terminology, which is the distance between P and the east cell in the x direction, would be equal to del x e, and this would be del x w, this would be del y north, and this would be del y south. All those terminology would be valid here as well. I am not repeating those terms here. Okay, so assuming that we are not interested in right now in the unsteady part, we can write the steady convection diffusion equation like this. So basically, del dot rho u bar phi equals del dot gamma grad phi plus s phi. That is basically the same equation that we have here. However, we notice that we have now introduced a new variable, right? That is your that's your rho, right? So this is a new variable that we have introduced. Up till now, we only had gamma, that is the diffusion coefficient for the flow. Right now, with convection, we are introducing the density of the flow field. Okay, so we also saw that density gets introduced even if you have an unsteady term in the past lectures, right? So that's what we have already seen. So it is good to keep in mind that the rho is introduced. Okay, and then the velocity vector that we have, that is u bar, I can of course write it as I times I hat times u plus j hat times v. Okay, so we have basically two scalar components u and v, and u bar would be the velocity vector. That is in this particular case, as far as the solution is concerned, this is basically is known, right? So basically u is known, right? U bar is known, right? For the solution of general scalar transport equation. Okay. All right. Then what is the first step in finite volume method? The first step is basically to integrate the convection diffusion equation on a control volume. That is basically this control volume. That is, if I integrate this, you have integral Cv del dot rho u bar phi dv equals, on the right hand side control volume, del dot gamma grad phi dv plus integral on the control volume s phi dv. Right. Okay. Again, what we know is we already know how to solve for the diffusion part, right? That is del dot gamma grad phi dv plus s phi dv equals 0 is what we already know, right? So we already know how to solve for this term, right? We already know solving for this term. Okay, so we will not worry about that part. Rather, we will worry about the convection term, that is del dot rho u bar d phi dv. So we will invoke the Gauss divergence theorem just the way we have done it for the diffusion term here. We will do it for the convection term. So invoking the Gauss divergence theorem, the convection term here can be rewritten as instead of a volume integral, we can convert it into a surface integral of rho u bar phi dot dA bar, right? So dA bar is now your area vector, and again assuming that this quantity that we have is a constant on the faces that this control surface is made up of, and that constant can be represented using the phase centroid value, we can transform this continuous integral into a discrete summation of sigma over f rho u bar phi sub f dot af bar, right? Where af bar is basically the area vectors for each of the faces, that is east, west, north and south, which we already know, right? Okay, so for example, what would be A east bar? A east bar would be delta y times I cap, right? Similarly, A north bar would be delta x times j cap, right? All these things are already known. Okay, so now we have to focus on basically evaluating this quantity, right? That is basically rho u bar phi f dot af bar on all the faces. So once we know how to solve this, then we can actually solve for the convection diffusion equation. Okay, so let's move on with our this quantity. So we can rewrite this quantity as basically we say sigma f rho u bar phi f dot af bar, right? And we also have to realize that this term, this particular term, is on the left hand side of the original equation. Okay, so if you go back to the equation, the entire diffusion and the source terms are on the right hand side, whereas this convection term is on the left hand side. Okay, so this is important because when we try to assemble the coefficients later on, then we have to know on which side of the equals equation is this particular term is, right? Because then only we can get the coefficient signs correctly. Okay, so we have the faces. The faces are basically east, west, north, south, and then the area vectors are all known. AE bar equals delta y I cap, AW bar equals minus delta y I cap, A north bar equals delta x j cap, and A south bar equals minus delta x j cap, right? So that we already know. And U bar is also known. U bar is basically U I hat plus V j hat. This is also already known. So can we write this one particular term of this summation? Out of the 4 terms we have, we will write first for the east face. So for the east face, this will read as rho u bar phi E dot AE bar, right? So this is basically, we know this thing as AE bar is delta y I cap, U bar is U I hat plus V j hat. So the only term that survives would be I dot I. So U times delta y is the only term that survives. V times 0, so that won't survive. So we can write this as rho u phi E, where U is this scalar component of U bar in the I direction times delta y, right? So now you know that this has to be evaluated on the east face, right? Okay. Of course, I can rewrite this as rho u evaluated on the east face times delta y times phi sub E, right? So phi value on the face E, little e, right? Okay. So now this quantity, if you look at this, is rho u delta y. This is basically the area. This is density. So density times velocity times area. What would this quantity be? This quantity is nothing but your density times velocity times area would be your mass flow rate, right? So that's your mass flow rate. We would like to represent it using a quantity F, capital F sub E. Okay, that is the mass flow rate on the east face is F sub E. Okay, so if I use F sub E instead of rho u E delta y, then I can write this entire quantity as Fe times phi E is what I can write this as. So that means one of the terms out of these 4 terms we have comes out to be Fe phi E, where Fe is the mass flow rate times phi is the scalar. Okay, so far so good. But what about phi sub E? Do we know the value of phi sub E? We don't know, because phi is only stored where? It is only stored at the cell centroids, right? It is not stored at the faces. Of course, we can somehow interpolate the value of phi east. That is what we would do. So that is what needs to be done. Okay, so how do we interpolate? For phi east kind of determines the kind of convection scheme we are talking about. Okay, so as far as the convection term is concerned, we got one term, that is Fe times phi east. Okay, now let us now look at the diffusion term as well, because when we write the equations, we want to introduce a slightly different notation than what we have used for the pure diffusion equation. So if you look at the diffusion equation on the right hand side, what we have is gamma grad phi f dot af bar, right? So for all the faces, again, if I consider the east face, this would come out to be delta y I cap. This has 2 components, so the only component that survives is the partial phi partial x, right? So this will be gamma e ae partial phi partial x on the east face. Now how do we calculate partial phi partial x on the east face? Using linear profile assumption, right? So now what you can see is that for convection, we need to use a model to calculate this dependent variable itself, right? So for phi east itself, you would need an assumption, whereas for the diffusion terms, you would need an assumption for the gradient of the phi, right? So that is the difference between the convection and the diffusion terms. For the dependent variable itself, here you would need a model. Here for the gradient of the dependent variable, you would need a model, right? So we have used a linear profile assumption, and we can write this as phi east minus phi p by del x e, and A east is nothing but your delta y, right? A e bar is your delta y I cap, but A east is your scalar value. So we have this value. Now, just like we have used a notation for the mass flow rate, that is multiplying phi little e as Fe, let us introduce another term for this coefficient, that is multiplying the phi capital E and phi capital P as the diffusion flux coefficient, that we call it as d sub e. Okay, so this is the diffusion flux coefficient on the east face, basically gamma e delta y by del x e, right? So if I plug in this, we can rewrite this equation as d sub e times phi east minus phi p. Okay, so far so good. So we have now looked at discretization of the convection term and the diffusion term on one particular face, that is the east face. Okay, all right. Let us also kind of define a non-dimensional number that would be an indication of the relative strengths of the convection and the diffusion terms. Okay, which we would call it as a Peclet number, which is based on the cell dimension. So we will call it as a cell Peclet number. Okay, so going by definition, the Peclet number, we would like to define it as the ratio of the convection to the diffusion coefficients, that is F to the D, right? Whereas we know what is the mass flow rate. The mass flow rate is basically Fe equals rho u E delta y, and the coefficient for the diffusion flux is gamma E delta y by del x e, right? So we can calculate now what would be the cell Peclet number. So this is rho u delta y upon gamma delta y by delta x, so delta y gets cancelled. So what you get is rho u delta x by gamma. Okay, so this is your cell Peclet number. We need this in order to know whether the problem is a convection dominated problem or if it is a diffusion dominated problem. Okay, depending on the value of the cell Peclet number. Okay, so that's going to define the relative strengths of these two physical quantities. Okay, all right. So we define this. Now let us get back to our discussion. Basically, we have now discretized on only for the east face. Now what do we have to do? We have to do the same thing. Essentially, we have to now introduce a model for phi east, right? And then once we introduce a model for calculating phi on the east face, we have to write equations for all the faces, that is for west, south and north, and then assemble all of these together and then put them in our form, that is AP phi p equals sigma A and B phi and B plus B. Okay, so that's what we're going to do next. Okay, now phi E is basically we need to write the face value in terms of the cell centroid values. That is basically where we have phi stored, right? Now how do we write this actually determines the convection scheme. Okay, so how we are going to write this is going to determine the convection scheme. Okay, so the convection scheme we would use would be based on how the phase phi value will be written in terms of the cell values. Okay, but for the phase gradient partial phi partial x, we have already introduced a model, that is the linear profile assumption, right? The linear profile assumption is already introduced. What is the linear profile assumption we have used? Can be called as, what kind of scheme can we call the linear profile assumption as? Maybe you have to kind of think and come back. Okay, now essentially once we introduce a convection scheme, once we decide on how we calculate phi east in terms of the cell values, what we need to do is we need to do write similar equations for the west, north and the south faces, collect all the terms and then formulate the final discrete equation for every cell. Okay, that's what we would do. Now that means we would introduce one particular scheme which we call it as a central differencing scheme. Okay, and now assume that we have a uniform mesh. Okay, if we have a uniform mesh, then phi sub E can be written as phi east plus phi p by 2. Now this we can write assuming that phi varies linearly between the cell centroids, which is also the same assumption we have used in evaluating the phase gradients. Okay, so if you have a uniform mesh and if you assume that phi varies linearly between the cell centroids, we can write the phase value phi little e as phi capital E plus phi p by 2. Okay, very good. Well, we want to do this because our eventual equation is in terms of the cell centroid values for phi p, phi east, phi north, and so on, right? Only then this can go into the matrix, right? Okay. All right. So, so this particular scheme of taking it as a linear average is known as central differencing scheme if you have a uniform mesh. Otherwise, this will be basically in terms of the linear interpolation, right? Okay. Now, if you introduce this, then what will happen to the convection transport through the particular phase E, through the phase east? The phase east, the east phase has basically the convection term is Fe times Phi E, right? So that's what we have. We have reduced rho u bar phi dot E dot A bar as Fe times Phi east, right? Now, if I introduce Phi east equals Phi E plus Phi p by 2, then I can write this Fe Phi E as Fe times Phi east plus Phi p by 2, right? That is I'm just substituting for Phi east as Phi east plus Phi p by 2. Now, what about this coefficient F sub E? Is this known or unknown? This particular Fe equals rho u E delta y. Is this known or unknown? This is known because density is known, area is known. For the purpose of the convection diffusion equation, we know that the velocity vector is also known. Okay, so essentially this coefficient Fe is known, and so is the diffusion coefficient dE. Okay, so these two are known. Fine. So we have now introduced a model for the east phase. Can the same model be extended for other phases? For example, for the west phase? Yes, this can be. Only thing is that for west phase, phi w would be half of phi w plus phi p by 2, right? Okay. So if we do the same thing, we can now formulate the total problem. Okay. So coming to the discrete equation, so the total discrete equation would read as bringing the convection term to the right hand side. Okay, so earlier this was on the left hand side with equals these two, right? Now I brought this to the right hand side with a minus. So what we have is sigma f gamma grad phi f dot af bar minus sigma f rho u bar phi dot af bar plus sc plus sp phi p times delta vp. Okay, now you already know this last term and the first term, right? This is what we have been doing in the diffusion equation. Now the only extra term is this one, which is rho u bar phi times dotted with af bar. Okay, that is the only extra term. All right, now let us consider only the east phase. Okay, let us consider only the east phase and also only consider these two terms, the diffusion and the convection. So these two would read it as gamma grad phi E dot ae bar minus rho u bar phi E dot ae bar, right? That's what we have, and we have written this diffusion as using linear profile assumption dE d sub E times phi east minus phi p, and this as Fe minus Fe times phi east. Okay, so if you plug in these two, what we get is for dE we have gamma E delta y by del x E times phi east minus phi p minus Fe times phi little e is phi east plus phi p by 2, right? This is what we have for these two terms. All right. Now, can we write a similar expression for the west phase? Yes, we can. So this is of course a mistake. This has to be supposed to be W. This should be W. Okay. Okay. Now this would be gamma grad phi W dot AW bar minus rho U phi W dot AW bar. Okay. So that would be equal to what would be this quantity? This would be minus, why minus? Because AW bar would be minus delta y I cap. So this would be minus gamma W delta y by del x W times grad phi partial x on the west face would be phi p minus phi W by del x W. And then here also AW would be a minus delta y I cap. So that minus and this minus would make it a plus. And this we would call it as FW. FW times phi W would be what? phi little w would be phi capital W plus phi p by 2, right? That's what we have. Now notice here we got a minus, here we got a plus. Similarly, here we got a plus and here we got a minus here. Okay, so there is some small difference between the east and west. Okay. Now, what is the definition? Fw is rho u w delta y, and of course aw bar equals minus delta y I hat. Okay. So with these two things, we now kind of wrote for the west face as well. Can you write for the north and south faces similarly? Yes, you can write, but we have to keep in mind the corresponding plus minus signs. So maybe you should try writing it out as well. Okay, as a verification. As of now, I'm going to assemble all of these things. Okay, so this is basically d little e, right? This is d little e times phi east minus phi p minus f east times this thing. Okay, and what about this thing? This will be minus dw times phi p minus phi w plus fw times phi west plus pp by 2. Okay. So if I assemble all of these things, what do we have? We have d east, phi east minus phi p minus fe times phi east plus pp by 2 plus dw. Okay, here I have changed the phi w and phi p, the order of phi w and phi p. That's why I could get a plus here instead of minus. Okay, and we have plus fw phi w plus phi p by 2 plus the north would be similar to the east face. Okay, this is what we have to verify. Okay, the north would be d north phi north minus phi p minus f north phi north plus phi p by 2 plus what would be the quantity for south? South would be, this would actually, south also would come out to be minus gamma delta x by del y south, but I would write with a plus with these two flipped. Okay, so this would be d south minus phi p plus fs times phi south plus phi p by 2. So this is basically coming from your diffusion terms and the convection terms, and we have of course the SC plus SP phi p times delta Vp equal to 0. Okay, so this is the final equation. Okay, all right, but what do we want our equation to be written as? We want it to be written as AP phi p equals sigma NB phi NB plus B, right? So what should I do now? We have to send all the phi p coefficients and phi p to the right hand side and leave all remaining things on the left hand side. Okay, so if we do that, what will be the coefficient for phi east? Phi east will get dE minus phi east will get fe upon 2, right? That's what phi east will get. Okay, what about the coefficient for phi p? When you send it to the right hand side, this becomes a plus and this becomes a plus as well. For phi p, that will be dE plus fe by 2 would be the coefficient for phi p, and the coefficient for phi east is d east minus fe by 2. You see there is a difference between the coefficients now. Okay, so if I were to write it as AP phi p equals sigma NB phi NB plus B, the coefficient for A east would be this east. Phi east remains on the left hand side, so this will be d east minus fe by 2. Okay, and A west would be dw plus fw by 2. Okay, A north would be d north minus f north by 2, and A south would be ds plus fs by 2. Okay, very good. Now what about AP? AP basically has a similar contribution, but these plus minus for fw getting flipped because consistently for all the diffusion terms phi p has a minus, right? So that takes care of the same term for same coefficient as here, but here we see that phi p has a plus. So as a result, this part of the convection that's going into the contribution of the neighboring coefficients would change its sign when it goes to the coefficient of AP, right? Okay, so what is the coefficient for AP? AP would be dE plus fe by 2, because this goes to the right hand side, this becomes plus, and then dW minus fw by 2 plus dn plus fn by 2 plus ds minus fs by 2 minus, of course we have our sp delta v as well, right? this becomes minus. Okay. Now what do you see here? What you see here is basically AP is not the summation of the neighbors, isn't it? Because you cannot write this as summation because this is minus, whereas you have got a plus. Here you got a plus, you got a minus. So when you had only the diffusion term in there, then this could have been, this was written as AP equals sigma A and B, right? But now it is not the case. But we have only different values here. Of course, we can now make it actually a summation of A and B by adding and subtracting certain quantity. That is nothing but this plus half FE by 2 can be written as FE minus FE by 2, right? I can write this. Similarly, this minus FW by 2, I can write it as minus FW plus FW by 2, right? I can basically add and subtract these quantities, okay? So I can write like this, and in which case dE plus FE by 2 is written as dE minus FE by 2 plus FE, right? But then this quantity is now what? This quantity is nothing but your A east, right? This is nothing but your A east. Similarly, this quantity is now nothing but your A west, and this is your A north here, and this quantity is now your A south. Okay. Of course, now we have introduced these extra terms which have to be taken out. So this is F east minus FW plus F north minus F south is the extra term that we have introduced in the process. But nonetheless, we can write now AP as A east, A west, A north, A south summation minus SP delta V plus these extra terms, right, that we have introduced. For example, what are the extra terms that we have introduced? We have introduced this quantity, this quantity, this quantity, and this quantity. Okay, these are the four quantities, that is F east minus FW plus F naught minus F south. Okay, so this entire thing is extra which we have introduced, but barring this, AP is now equals sigma and B minus SP. So this particular quantity has some significance which we will see in little while. Okay. What is this quantity? FE is the flow rate, mass flow rate through east phase. FW is also mass flow rate through the west phase, and F north mass flow rate through the north phase, and F south is the mass flow rate through the south phase. Okay, so that means mass flow rate through east minus west plus north minus south. That is the quantity we are talking about. Okay, very good. All right. Then what is our B? B of course is your SC times delta Vp, and AP is your now sigma A and B minus SP delta V plus this quantity. Okay. Now, because these are all the mass flow rates through the phases, right? So these are basically the mass flow rates that are going out of the domain. Let's say if your U is positive, U and V are positive, then this is the total mass flow rate that is going out of the control volume, right? Because rho U delta Y is, U is positive, then it is basically rho U bar dot AE bar, right, which will give rise to rho U delta Y. That will be a positive quantity. So that means this entire thing is basically the net mass that is entering and leaving through the control volume through all the phases. Now, if the given velocity field U bar, Ui plus Vj satisfies continuity, let's say if satisfies mass conservation, then what will this quantity be? The amount of mass leaving through the east phase minus the amount of mass, essentially this is the amount of mass entering through the west phase, plus the amount of mass leaving through the north phase, and the amount of mass entering through the south phase. This is basically the conservation of mass, right? This has to go to 0 if the given velocity field U bar satisfies continuity. Okay, so that means this would be 0 if you have a velocity satisfying flow field that is given to you, for which you have to calculate the transport of the scalar. Okay, so that means this quantity would go to 0 if you have a continuity satisfying velocity field. Okay, that you have to verify once again. All right. Now, okay, so now in all these quantities we have just listed out what is DE and FE, but the definitions are, we already know, right? T east would be gamma E delta y by del x E, D north would be gamma N delta x by delta y north, and similarly F east is rho u east delta y, F west would be rho u west delta y, F north would be rho v and delta x, and so on, right? So these are all known values because density is known, velocity is known, diffusion coefficient is known. Okay, so all these are known. Fine. So essentially we have now formulated the equation. Let's make few comments. Okay, the comments are, now AP is not just summation sigma A and B minus SP delta V like what we have seen before, but we have this extra quantity. Okay, and what about the coefficients? The coefficients are A east equals DE minus FE by 2, where DE and FE are known. Similarly, A north is D north minus FN by 2, where DN and FN are known. Okay. Now, what about the coefficients? Do the coefficients look okay? They don't really look okay, because if you consider, let's say your velocity field is some 2 times I plus 3 times j, where u and v are both positive quantities. Okay, so basically your velocity is going in the positive quadrant direction, right? It's basically has 2i plus 3j, it's going something like this. Then that means if you have this, your all your flow rates are now positive, right? Because your u east, u west, u north, v north, v south all are positive, so these are all positive quantities. And diffusion is always a positive quantity, right? Then is this coefficient AE always positive? Need not be, right? Because if FE is greater than DE by twice of DE, then this actually can become negative, because these two are positive quantities now. DE is positive, FE is positive, but the magnitude of FE can be more than, if it is more than 2 times DE, then this coefficient becomes negative, then AE becomes less than 0. Similarly, if F north is greater than 2 times D north, then even A north can become, this should be A north, okay, so this should be A north can become negative, right? Now, of course, I have assumed that the u and v are here positive quantities. If you assume u and v are both are negative quantities, then instead of A east and A north, you would get A south, A west and A south to be the quantities that may become negative, right? Because if you go back, if you assume u to be negative, then this always becomes positive and this always becomes positive, whereas this will become now negative, right? Because u is negative, so your FW would come out to be negative and this would come out to be negative. Okay, all right, so that still happens. So that means what we have is, we have the coefficients are not guaranteed to be positive, and the coefficients are not guaranteed to be positive depending on the relative importance of the convection and the diffusion. Okay, that's what we see. Okay, what about the Scarborough criteria? If these becomes negative, what will happen to Scarborough? Okay, let's say we source is 0, and if we have continuity satisfying flow field, this is 0. Some of the coefficients A and B are negative, so AP will be equal to sigma A and B, because you have, let's say, some coefficients -2 plus 3 -1 plus 2, something like that. You would get some value of 2 or something for AP. Okay, AP will be equal to sigma A and B, but the Scarborough criteria would be modulus sigma of sigma A and B by modulus of AP. This will not be satisfied, because now AP will come out to be smaller than some of the modulus of the negative values, right? The moment you have negative values, although AP equals sigma A and B, this will not be satisfied, right? This will be less than or equal to 1, will not be satisfied. So with the negative coefficients, your Scarborough is not satisfied. What about boundedness? Your boundedness is also not satisfied, because now A and B, some of these are negative. As a result, your boundedness is also not satisfied. Only if you have all positive quantities, the phi p value will lie between all the phi and b's, right? Okay, so that means your Scarborough and boundedness are not going to be satisfied. As a result, you cannot solve for this if your coefficients become negative. Okay, so in order to make sure that the coefficients do not become negative, of course we have to do something like this. We have to choose always FE is less than 2 times DE, That means Fe by dE is less than 2. But of course, we know what is F by D. F by D, we have defined it as a Cell-Peclet number. So Cell-Peclet number has to be always less than or equal to 2. But what is the Cell-Peclet number definition? The definition is rho u delta x by gamma. But what is known and what is unknown in this? Velocity field is given, so you cannot change it. You cannot say I will solve for a different problem. Density is also known. Gamma is known, right? So the only control you have is basically delta x. You have to choose your mesh such that your delta x is such that this comes out to be less than 2 gamma by rho u. Okay? Only then your coefficients will not become negative, and as a result, you can use central difference scheme for solving for convection diffusion equation. Okay? This actually puts a very stringent restriction on the mesh because your gamma is usually very small, and depending on how large your velocities are, your delta x has to be made much finer. Okay, so as a result, the central differentiation scheme for convection equation comes with a very big restriction on the mesh size that you can take in order to solve for it successfully without having any divergence. Okay. Okay. So, all right. All right, then that's all for today. So I'm going to stop here. So in next class, we will see another discretization scheme for the convection term. That is basically your upwind differencing scheme, which will not come with a similar kind of, which will not have these kind of restrictions. So we're going to look at that in the next class. All right, thank you. And if you have any questions, write back to me on my email, okay? Or else we will see if we can set up a Google chat or something like that. All right, thank you. See you. Talk to you in the next class.